Let's look at special applications of the tricks we have learned to deal with separable variables. So, first of all, when you're looking at an ODE, if you don't know where to start, or even if you know where to start, your first step should be finding the equilibrium solutions. It's usually easy and it gives you a baseline. What sort of baseline does it give you? Well, it gives you the idea that if something is tending towards an equilibrium solution, it's going to stay there. It allows you to block things around. So your first step when you're dealing with things should be to find equilibrium solutions. Then you can look at situations in which your ODE is not separable, but has a specific format. We're looking at a format that is y prime equals a fraction between two functions in which both the numerator and the denominator depend on both x and y. And it might seem counterintuitive, but for a second bear with me. Instead of considering y as a function of x and x being an independent variable, we want to consider y as a function of t, another variable that we haven't used yet and of which we know nothing about, and x as a function of t as well. Why would that help out? Well, we can rewrite y prime as dy over dx. Then we can divide both sides by dt, so we rewrite y prime as dy over dt, all of it over dx over dt. But we know that y prime is equal to the fraction between f and g, so we can write dy over dt divided dx over dt equals f over g. If we do this rewriting, then we can say that we can separate our ODE into two new ODEs. dy over dt equals f of xy and dx over dt equal gxy. So we changed having to solve an ODE into having to solve a system of ODEs. So we have to solve for y and x at the same time. Why does it work? It works because the new system implies the old system. So in some senses, we're making things more complicated in the hope that in the new system, in this ODE system with x and y both being dependent on t, we can have something easier.